Hello everyone. In this video we are going to talk about the important notion of singularity or singularities and then singularity decoupling in specific conditions for 60OF robots. So what is singularity? Why are they important? Well, if you remember when we talked about the Jacobian matrix, I showed you that the end effector velocities, all linear and angular velocities, zeta, can be written as what? A linear combination of the columns of the Jacobian matrix, correct? So if your Jacobian matrix J, which has a dimension of 6 by n, if you write it as a bunch of columns, J1, J2, all the way to Jn. Each one of these is a column vector, and the dimension for each one of these is 6 by 1. Okay, so here, these are the columns of the J matrix. When you multiply, you say zeta is equal to J times vector Q dot. When you expand this, then you see that you can write zeta as a linear combination of these columns, where the weights for those combinations are what? The angular velocity for each one of the joints. Good? So we know about that. Great. Now, what do we know about linear combinations? So, if we want our manipulator to be able to move its end effector in 3 different directions, x, y, z, and rotate it about the 3 directions, theta x, theta y, theta z, so your end effector has to have 6 separate degrees of freedom, right? And now the question is, when I'm getting that through the combination, linear combination of J1, J2 all the way to Jn, can I ensure that I get all those 6 degrees of freedom or not? Well, for example, if my J looks something like this, if you remember, let's look at this one actually. This is a good one. The J for the 2DOF planar arm. My J looks like this. So this is J1, column J1. This is what? J2. Now when I have this, can I expect my end effector to have all 6 velocity terms, correct? Can I get all of that? The answer is no. Why? Because if I look at the 3 columns here, the 3 rows, I'm sorry, this one, and this one, you clearly see that it's impossible for me to get z dot component, omega x component, and omega y component. It is impossible, okay? So absolutely not. It's not possible. Then this 1, 1, if you remember, we also discussed this, and I showed you that really this is also impossible to achieve a separate omega z. If you can determine x dot and y dot independently, omega z is automatically determined as q1 dot plus q2 dot. So this one is not really going to be independent. So now let's just focus on this 2 by 2. You might say, well, why don't you trim it like several times in the past? Why don't you just focus on this 2 by 2 portion of this J? So for the moment, say, well, J is only this matrix, okay? Let's just throw away the components that I know it's impossible for me to achieve, okay? Just focus on the x dot and y dot I know I can achieve. Now, the question is this. Let's just focus on this, fine. Can I claim that I can achieve now any x dot and any y dot I desired if my manipulator it is at any arbitrary angle combination? Because you clearly see my Jacobian is a function of what? The angles, correct? So if I put my theta 1 and theta 2 at any number I please, and then if I ask my end effector to achieve any x dot and what? Any y dot that I want. So that's the velocity of the end effector. Can this always give me an answer? Can I always find a q1 dot and a q2 dot, or a theta 1 dot and a theta 2 dot, which give me arbitrary x dot and y dot for arbitrary theta 1 and theta 2? The answer is no. There are some combination of these angles for which both x dot and y dots, or the two vertical motions the two perpendicular motions in general, is not possible. And you might say, when? And the answer is this. The answer is when this guy that you see, this trim J, is losing rank. What does rank mean? You know from linear algebra, rank means the number of linearly independent columns. So here you have J1 and J2. Are these two columns always linearly independent? Are these two columns always linearly independent? If they are, then rank of this matrix is always 2, or determinant of that is, in other words, since it's a square matrix, you can talk about determinant. Okay, determinant of that is non-zero, right? So when I want to find q dots, you can simply what? Multiply the inverse of the J matrix by the given zeta and get what? The q dots that you were after. Okay, so again, if the matrix is full rank, it means when it's a square, you can also say the determinant is non-zero or the inverse does exist. So rank is good for rectangular, really, in general, but if it's a square, we can talk about the determinant. So the question is, does the determinant of this J ever go to 0 for any combination of theta 1 and theta 2? If that's the case, this J inverse does not exist, and that means I probably would not be able to find any unique solution for q dots, okay? Or it means if I have my q dots, I will not be able to get any arbitrary zeta, okay? So clearly you see the meaning of singularity. So if I want to write down a definition for singularity, singularity is what? Those configurations in the robot for which the Jacobian matrix loses rank. It's not full rank anymore, right? It is what? It has a rank less than full rank. For those configurations, we call them singularity, and in singularity, so many things can happen. What are they? We're going to go through this item 1 to 5, and I'll show you what are the consequences of being at a singularity configuration, okay? But for now, again, if I want to write down something, I would say at singularities, the Jacobian matrix is not full rank, which means what? Means it does not have n linearly independent columns. Okay, so that's a simple definition that you can provide for singularities, that at singularities you won't have n linearly, because you see, in general, you have n columns. You're not going to have all of them linearly independent. Some of them will depend on some others, or it's a combination of some others, okay? They are not all linearly independent. And since I'm not sure how good you are with linear algebra, in robotics you have to be very good with linear algebra, okay? But since I'm not sure, I define that for you here, because I really want to make sure you understand every single word that I'm saying, okay? That's how I teach. I hate to be saying something when I know my students don't understand it. So what's the meaning of linearly independent? When is it that I can say that vectors x1 and x2 and all the way to xn are linearly independent when what? When the linear combination of them, a1 x1 plus a2 x2, and a's here are scalars. We call them weights. These weights a1, a2, a1 x1 plus a2 x2 plus all the way to an xn, this combination is equal to vector 0 if and only if, IFF means if and only if, what? All of these gains are equal to 0. In other words, the only way that I can combine these vectors and set it equal to 0 is I use all weights of 0. Of course, if I use weights of 0, sum of all these zeros will be 0. But that's the only solution. I cannot, for example, have 1 times x1 plus 2 times x2 plus a bunch of other things plus, let's say, 5 times xn equal to 0. If I can find non-zero weights, even if one of them is non-zero, even if one of these guys is non-zero, if I can find any combination like that, okay, if I can find any combination like that, where even one of these gains is non-zero, it means these guys are linearly dependent. Why? Because from here, I can find one of them based on everything else. I can say, well, if I want to make xn, how do I make it? I say xn is equal to what? It is equal to negative 1 times x1, negative 2 times x2, and the rest of the terms, and then divide everything by 5. So you see, xn is negative 1 over 5 x1, and then what? Negative 2 over 5 x2, and some other numbers times the rest of them. So by a linear combination of the other vectors, I can find xn. In other words, I don't need this vector independently from the others. Once I have the first one, second one, third one, all the way to n minus 1, I can easily find this one by combining them linearly. So this is not independent from the rest. It's like, for example, if you have vector I and vector j, right? Now, if I give you something like this, can I also say this one, which is like 3i plus 2j, is this vector also linearly independent from these two? No, because this vector v clearly can be made by a linear combination of I and j. So the only vectors I can have in 2D that are independent from each other are something like I and j, or something else that is, for example, perpendicular to that vector. Okay, so how many linearly independent vectors I can have? Well, it depends on the dimension in general, the dimension of the space, but that's the overall idea of linearly independent, which is the only way I can make a 0 out of the combination of these vectors is I use gains of 0. If any of them is non-zero, then they are linearly what? Depending on each other. Okay? So that's the idea. I just wanted to make sure that you know it. Good. So now that's the same thing here. I'm linearly combining these columns of J using which weights? Using these Q dots. These Q dots here are like those A gains, and your J's are like those X vectors. So I'm combining them and getting this guy. Now, if one of these J's is not linearly independent from the others, so instead of n linearly independent columns, I have like n minus 2, which means 2 of them can be found based on the others, then I'm not going to have n columns independent. I have n minus 2, and it means really this guy is not going to have all 6 degrees of freedom. It is only going to have 4 degrees of freedom, really independent. In 4 directions you can move it or rotate it. In 2 directions it's not possible. Okay, and let me say one more thing about the rank. So if your matrix is A m by n in general, I said rank is good for rectangular matrices. The rank of A is what? It is always the minimum of m and n. Okay, so if it's like a 6 by 8, right, then the rank can at most be 6. It can never be the bigger number, right? So when your J is 6 by n, what is the rank? Well, the rank is the minimum of 6 and n. So if you have less than 6 joints, then it is n. Like for example, for this 2DOF robot, rank is what? This is a 6 by 2. The max rank then this guy can have is 2. For Ascara, it's 4. For a 6DOF robot, it is 6. If it has 8 joints, then you never go beyond 6. So the max that J can have, the max, it is 6. It never goes beyond 6. And that's why, because this zeta at most can move in 6 directions. So you clearly see that the degrees of freedom in zeta is directly related to what? To the rank in J. The rank drops in J, it means the degrees of freedom along which zeta can move or rotate drops, and that is called singularity. Okay, so you see I'm using all sorts of different languages to explain this notion to you. Good. So at singularities you lose a rank. Now if matrix is square, you can show that instead of the rank of J dropping, you can say also what? The determinant goes to what? 0, because now one column depends on another column, and you know in determinants, if one column depends on the other columns, determinant is 0. So now question, for what combination of angles this 2DOF has a determinant of J equal to 0? Is there any solution here, right? Is there any solution? And one solution can be quite obvious without me even needing to cross multiply here, calculate the determinant, and then solving that transcendental equation that you will get. One solution could be obvious, and that is what happens if your theta 2, the second angle, is 0, which corresponds to what basically? Corresponds to your robot being fully extended, correct? If your robot is fully extended, so here theta 2 is 0, what happens here? Well, then when you say C1, 2, this is cosine of 1 plus 2, but 2 is 0, so this is going to be the same as C1, and S1, 2 is going to be the same as what? S1, because 2 is 0. So what you do here is you make this one S1, you make this one C1, C1, and S1. And what happens to this J matrix? Well, your J matrix becomes, here if you factor out S1 and down below you factor out C1, you will get negative S1 times A1 plus A2, then negative A2 times S1, then C1 times A1 plus A2, and then A2 times C1. And you clearly, if you call this J1 and call that J2, you will see that the two columns are what? Linearly depending on each other, right? You clearly see here that your column J2 is what? It is A2 divided by A1 plus A2 with a negative sign, or no negative sign, times J1. So if you multiply the column J1 by this constant number, that will give you column J2. That means they are linearly depending on each other, and that means you're losing one rank, and your determinant is going to be 0, definitely, because you know determinant of a matrix that the columns are linearly depending on each other or combination of each other is 0, right? Hopefully you remember from linear algebra. And so it means J inverse does not exist. Now, when J inverse does not exist, what does it mean? So let's take a look here. If we go and plug this J here into my original equation, and then let's ask for some zeta. So let's say first I give it some zeta like this, and say, for example, this zeta, which in this case is the same as the v of the end effector, correct? Because that's simply x dot and y dot. I don't consider anything else here for the end effector. This, for the moment, let's say it is equal to, for example, 0.5 and 0.2 meters per second. Okay, so if I plug it here, you will get 0.5 and 0.2 to be equal to negative S1 times A1 plus A2, C1 times A1 plus A2, then negative A2S1 and A2C1. This times Q dot, which in this case is theta 1 dot and theta 2 dot. If I multiply and expand, I'll get two equations. Equation 1, negative A1 plus A2S1 theta 1 dot, negative A2S1 theta 2 dot is equal to 0.5. And then here, what? You will get A1 plus A2 C1 theta 1 dot, and then plus A2 C1 theta 2 dot is equal to 0.2. Now, can you solve this for a solution? Is that possible? So here, I'm sure you know it from linear algebra, but just to try it out, I just chose some numbers so we can try it also numerically in MATLAB. But here I chose my theta 1 to be like 30 degrees, just to try some numbers. And then I chose my A1 and A2 to be 0.4 and 0.3. And this is my zeta. And now I'm asking MATLAB to give me the solution by inverting J and multiplying it by what? By zeta to give me Q dot. So here, that is your zeta. This is your J matrix. As you can see, negative A1 plus A2 sine of theta 1, negative A2 sine theta 1, yes, and then A1 plus A2 cosine theta 1, and then A2 cosine theta 1. That's your J matrix that you can see. The determinant of that, if you look, is 10 to the negative 18, which is practically 0 in MATLAB. And then I multiplied inverse of J by zeta, and look at the numbers. It says the only way you can achieve it is by theta 1 dot and theta 2 dot to be something times 10 to the positive 16 radians per second. Right? And that is what exactly we are talking about here. That we asked for a bounded end effector velocity. We only asked for 0.5 and 0.2. But the answer it found for joint velocities are what? Unbounded. Okay, you saw that the Q1 dot and Q or theta 1 dot and theta 2 dot that I found were what? Very, very big, correct? This is something like 10 to the 16, and this is also like 10 to the 16. These are huge numbers which you cannot achieve, unbounded really. Practically, they are like infinite. Okay, so the problem is for the inverse velocity problem, you cannot find any finite number, okay? You cannot find that. That's one of the cases that happens in singularity. You cannot solve the inverse velocity problem. Similarly, you cannot also solve the case for the static force. Why? Because if you basically use just bounded joint torques, you might get unbounded end effector forces, right? So tau J transpose F. Let's take a look at that. Tau is J transpose F. Why is it that it says you can have bounded torques for the end effector, yet you get unbounded force at the for the joints, bounded joint torques for the joints, and get unbounded force at the end effector. So you're just applying 2 Newton meter to the first joint, 3 Newton meter to the second joint, but you see your end effector is applying a ton of force on the object and trying to crush it, right? So that's not something you want, right? And where does that come from? Well, from here, if I want to solve for F, what is F? Well, F is going to be inverse of this guy times tau. So it is going to be J transpose inverse, correct, from the left times tau. If, of course, J transpose does have an inverse. So for the moment, assume we are dealing with that 2DOF robot again, right? And so you know that transpose and inverse, you can change the order. So it is going to be J inverse transpose, really, times tau. And you know when J does not have what? An inverse, correct? When you use that J inverse, which doesn't exist, and you want to apply it to tau to get what? F, guess what happens? You're not going to get bounded numbers. Again, I can try it here for you, but you know what's going to happen, right? So here, I'm going to apply 5 Newton meter to the first joint. I'm going to apply 10 Newton meter to the second joint. And the question is, what are the Fx and Fy that the end effector is going to what? To apply, right? And here, as I said, I need to make sure that my robot is in a singular position with theta 2 of 0. So theta 2 equals 0. I use the same numbers as last time. I'm applying a tau 1 here, a torque here. I'm applying a tau 2 to this joint. And if this is in contact with something, right, let's say this is an object, this guy is going to apply 2 forces on it, Fx and Fy. The question is, how much is Fx, how much is Fy? And we see that it is J inverse transpose times tau. So let's do it. So let's say tau is equal to 5 and 10, correct? And then F is equal to transpose of inverse of J times the tau, correct? Boom. Some numbers times 10 to the 17. So this is going to be like 4 times 10 to the 17 Newton. And this is going to be what? 7 times 10 to the 17 Newton. You see? So bounded torque, small torques, led to what? Led to unbounded or practically infinite forces applied on the end effector. So if this end effector comes into contact with any object, can easily break it. Okay, so you see I cannot solve my inverse problem. In this case, we have infinite forces at the end effector, which is not desirable, right? So we have seen those, but there are other problems too with the singularities. Let me talk about the fourth item. It says singularities usually, but not always, are the points where your end effector is on the boundary of the workspace, or it is the maximum reach point of the manipulator. Okay, clearly you see it is the case for here. when you make your theta to 0, that's the maximum that your end effector can reach. Remember, if this one was A1, this is A2, the max you can reach was A1 plus A2, so that's definitely the end boundary of your workspace. And if you remember something else, when we talked about workspace, I showed you that if A1 is bigger than A2, if you remember that, then there is an inner ring as well here that your end effector cannot reach, and the radius for that was A1 minus A2. So if your end effector comes back on this ring also, it probably corresponds to another singularity. And under what condition you would reach this? Yes, you are right. You will reach that when your link number 2 completely comes back, like this. Okay, when your robot is like that, right, which means theta 2 is equal to pi, then that end effector will be on the small circle. Now the question is, when I make theta 2 to be pi in this matrix, am I still going to get a singular, a J that is losing rank, that is not invertible? And the answer is yes, absolutely. Take a look here. So that was J, right? With only what? With only theta 1, correct? Now let me do the same J, but this time I do it with theta 1 and 2. So if you remember, in general, it is what? It is A1, C1, A2, C1, 2, right? So the first one is A1, the next one is A, so it is going to be simply negative 0.4, which is A1, and here A1 is 0.4, A3 is A2 is 0.3, so it is smaller than A1, so you are good. That is the first one, and then minus, correct, A2 sine of 1 plus 2, and 2 is 180, so that is your first element. Your second element is simply negative A2 times S12, which is this guy. Then we see if it allows me to go to the next line, or it's going to pick on me. Okay. I had to first take this off, and then this one is going to be A1 times cosine 1, and then plus A2 times cosine of 1 plus 2, and the last element is simply A2 cosine of 1 plus 2. So this is your J matrix, and now if I say what is inverse of J, you see that the numbers are huge, or if I say what is determinant of J, you see it's practically 0. So it doesn't matter whether theta is 0 or pi, because your end effector is on the boundary of the workspace. For both of these, your solution is not going to exist to the inverse problem, to the static problem, and so on. So this robot in general has two singularities. One of them is theta 2 is equal to pi. The other one was theta 2 was equal to what? To 0. These are the two singularities of the 2DOF robots, which you can also find if you set the determinant of this guy equal to 0 and try to solve that transcendental equation, right? So let me get it. I tried to avoid it so far, but if you want, I can do it. It's not really such a hard thing to do. So determinant of J is the determinant of this. What is it? Well, it's the diagonal product minus the anti-diagonal product. So you will get negative A1, A2, S1, C12, then negative A2 squared, S12, C12, minus the product of those, where the product of those is negative A1, A2, and then C1, S12, and then you have negative A2 squared times S12, C12. This whole thing should be 0. Now, when you apply this negative to both of these, they all go positive. And if you look now, this positive A2 squared S12, C12 with this negative of that term would go away. These other two terms, they both have A1, A2 in them, these guys. And the other hand side is 0. So what I can do, I can get rid of this A1, A2. And all will be remaining is what? C1, S12, and then what? Minus S1, C12. This has to be equal to 0. And now what is this? Well, if you know, in general, when you have a formula like that, right, the sine of one times cosine of the next one minus sine of the second one, cosine of first one, this is sine of this guy minus this one. So it is sine of 1 plus 2, and then what? Minus 1. This has to be equal to 0. So this one is the argument for 1, 2, and this one is the argument for 1. And what is this? Well, these guys go away. You get sine of theta 2 equals 0. And guess what? The answers are theta 2 equals 0 or theta 2 equal pi. Okay, so mathematically also finding the singularity in this case is not such a big deal, but I showed you also physically what happens when your theta 2 is any of these two angles that they are on. And it says not always. I'll show you cases that the singularity can be inside the workspace, not on the boundary of the workspace. So there are scenarios that it's inside the workspace. I'll show you that when it says not always. But I showed you items 1 and 2, 2 and 3, the unbounded velocities of the joint and the unbounded end effector forces. The other stuff we need to talk about, it says singularities are the configurations for which certain direction of motion are unattainable. And that's exactly the case again here. If you look at this, in which direction can I not move the end effector? And the answer is in this direction. If you want your end effector to move in that direction, which is the extension of the two members, that kind of motion, if I say I want my zeta to be like that, there is no solution for theta 1 dot and theta 2 dot to make it happen. There is no solution, absolutely not. Now, what is this zeta? Well, if it has some magnitude v, you can write it as v, since this angle itself is theta 1, you can write it as v times cosine theta 1 is the x component of it, and then the y component of it is going to be v times what? Sine of theta 1, correct? So if I go back and solve this problem that we did last time and we got these huge numbers, I redo that, but instead of 0.5 and 0.2, I plug in these numbers. Some fixed number times cosine 1 and times some fixed number times sine 1. Let's see what we get. Okay, so let's go back here. And this j that we had earlier, where was that j? I guess it's here, right? Is that the j? Yes, this is the first j that we defined. And my zeta, I changed my zeta. So let's say v is whatever you want. Let's say 0.4. And then this is going to be cosine d of the angle theta 1, which we consider 30 degrees. and then also 0.4, which is V times sine D of, again, 30 degrees, right? Correct? That's what you have, correct? Now, if I say what is inverse of J times zeta, correct? That's the solution. Again, you see, the only way that you can achieve it is using infinite numbers, right? Which is physically not possible. And then you might say, well, what's the difference between that one and if you used a different thing? Well, nothing really. If I used a velocity other than this also, correct? You saw that with 0.5 and 0.2, which were not along the 30-degree angle, I still could not achieve it, okay? It's not possible because all you can do at the moment is to only move in this direction, right? Or if you see it horizontal, it might be even easier to see. If it's all horizontal, so theta 1 is just 0, can I ask this end effector to go in that direction? No, it's not possible because I'm on the boundary of the workspace. I cannot go any further. So the fact that it says the boundary of the workspace, some directions of motion are not attainable, that is clear. Why are they not available? Because now I lost rank. And if you remember, I told you some important thing. When J loses rank, what does your zeta lose? The degrees of freedom it can move. Right? If he loses 2 ranks, this guy loses 2 of the 6 velocities possible to it. 2 of them will be lost. 2 of them you cannot achieve. Okay, so that is very, very clear. And then it says there is no unique solution to the inverse kinematics problem. Right? In such case, there may be no solution or infinitely many solutions. And again, that's very clear if you look at this example again. So if I give you this robot completely extended, right? I don't know my theta 1, but I know my theta 2 is 0. And if I say, okay, I want, and let's say this is A1, this is A2. If I say my end effector, I wanted it to be, let's say at this point, can you change your theta 1 and bring it here? But keep theta 2 at 0. Is that possible? The answer is no. Because now, by changing theta 1, all I can achieve is the points on this circle. That's all I can achieve. These two links, when theta 2 is kept at 0, they act like one single member. So, if this point that I'm asking the end effector to go, if this x of e and y of e, if they are on this circle, then there is what? How many solutions exist? If it's generally on that circle, then you can have all sorts of different ways to achieve it, right? Yes? Is that correct or no? Well, depend on the point. No, if this point is just here, then you only have what? Really one theta, correct? Right? There is only one theta that make it creates a singularity. Theta 1, you fix it, and it gives you one solution. But that's an exceptional case. If it's not on the boundary and I ask, how about this? Can you get that? Well, of course not, because my end effector is only on that circle. So you see, it says near the singularity. It doesn't say at the singularity. That's the key word that you have to pay attention. That near singularities, there will not exist any unique solution. So near these positions, even if I'm a little bit off of that circle, can you give me a solution for theta 1? The answer is no, I cannot. If I'm at the singularity, then I might be able to find one unique solution, right? But if I'm near the singularity, then there will be no solution to the inverse kinematics problem. So you see, these are all of the things that will happen at the singularity. Basically, your whole system would collapse, right? You cannot find solution to anything, to the inverse velocity problem, to the inverse kinematics problem, to the statics force analysis problem, right? Correct? You cannot achieve in motion in specific directions and so on. So these are all of the limitations when your J matrix loses rank, or if it's a square, the determinant of it goes to 0. These are the points you should avoid at all costs. It's not a good idea to be at those points. Okay, so here is one example. Now, very fast, I want to talk about another topic, and that is called decoupling of singularities. What does that mean? Well, if and only if I have a 6DOF robot and it has a spherical wrist, so I have some condition. My robot has 6DOF, so my J is 6 by 6, and it has a spherical wrist. So the axes of the last three joints are all intersecting at a single point. If you remember, we called it what? The wrist point. Very well. Then this 6 by 6 J, if I write it as 4 sub matrices, J1, 1, 1, 2, 2, 1, 2, 2, where each one of these guys, each one of them is a 3 by 3 matrix. Okay? Then what happens here? Well, you know, if you have a matrix J and it has sub matrices which are all square also, if I ask you what's the determinant of J in this scenario, what is it? What would you say? You can treat it like a 2 by 2 matrix, although what? These are clearly matrices themselves, they are not numbers. So determinant of J is going to be determinant of J11, correct? Times determinant of J22 minus determinant of J12 times J21. So you can treat it like that. Good? Now, if it's a spherical wrist, the last three centers of the frames, which is basically 0, 4, 5, and 6, as well as 3, they can all be considered at the same point. So with the spherical wrist, I can say that O3 is the same as O4 is the same as O5, and if I neglect the small distance between this wrist point and the center of the end effector, I can say also this is equal to O6. So this last one depends on whether I can neglect that or not. If that is the case, it means these vectors here, all of them are 0. But what were those vectors, if you remember? Well, remember, when it's a spherical wrist, it means the last three joints are what? Yes, all rotary joints. And if you remember, when we talked about Jacobian, I said if a joint is rotary, the column of the J matrix associated with that rotary joint, Ji, is what? The top part of it is Zi minus 1 cross On, which is in this case is O6, minus Oi minus 1. And the last three numbers of it are simply Zi minus 1, correct? Just go look back at when we talked about Jacobian matrix using the DH convention. This was for a rotary matrix, for a rotary joint. And since the last three are rotary joints, they are all following this format. Now this portion for all of these joints will be 0, so it means the top three numbers for the last three columns are all going to be what? 0, 0, 0. These are vectors, okay? These are not scalars. These are vectors, 0, and they are all 3 by 1. Okay, so the zeros are all 3 by 1. And what does that mean? It means when you combine these, it is going to be a matrix of all zeros, and it is 3 by 3. And where is it? Since these are only the last 3 joints, you also have 3 more joints with their columns. It means this all zeros is going to be this guy here in your J matrix. It's this one, J1, 2. That is going to be a matrix of all zeros. So this 0 here is what? 3 by 3. And when your matrix becomes lower diagonal like this, then determinant of J is simply what? Determinant of J11 times J22, because J12 here, which you had, determinant of this is 0, so this whole term goes away. So what does that mean? It means determinant of the manipulator, Jacobian, is equal to determinant of its upper left corner times the determinant of its bottom right corner. But what are these, each one? What are these? Yes, this one comes from the first 3 joints. This is the effect of Q1 dot, Q2 dot, Q3 dot on what? What's the meaning of this JJ if I ask you? What are the components in this J11? It is a 3 by 3 matrix. So what's each column in that J11, correct? This J11, it has 3 columns. Each one of these columns is a 3 by 1. Right? Remember, your J1 itself is 3 by 3. What's the meaning of each one of these columns? Well, I'll tell you. If I call the joint velocities of the robot Q1 dot, Q2 dot, Q3 dot, all the way to Q6 dot, what's the meaning of this portion? This is what? And if I call your zeta to be x dot, y dot, z dot, and what? Omega x and omega y and omega z. What's the meaning of J11? J11 shows the effect of the first 3 joint velocities and their contributions to what? To the first 3 numbers in zeta. Which is what? These are the velocity, the linear velocities of the end effector. So the first 3 joints on the linear velocity of the end effector, on the position x, y, z, and its time derivatives. So the effect of these on those is determined by J11. What is J1, J22? J22 is the effect of the last 3 joint velocities on what? On the angular velocities of the end effector. So this is determined by the columns of what? J22, right? So J11 is talking about linear position and velocity. J22 talks about angular position and angular velocity. So when I set the determinant of the whole J is equal to 0, it means either this one is 0 or this one is 0. When this one is 0, it means those singularities that are for the position of the end effector. This means those that are for what? The orientation of the end effector. And that's the case. If we look at J11 and J22, when we set J11 equal to 0, so let me write it for you. When we set determinant of J11 equal to 0, if there is any solution to this, if there is any set of angles or joint values that give such a solution, we call those what? Yes, we call them position singularities. And when we set determinant of J22 equal to 0, we call it what? Orientation singularities. or we might call them the wrist singularities. So the total singularities of the manipulator is what? Is the singularities for what? From the first three joints and the effect of them on the position, plus the ones from the last three joints and the effect of them on the wrist. So I could separate the total manipulator singularities into the combination of two separate things: position singularities and orientation singularities. The fact that I could separate these guys from each other, I call it decoupling. We call it singularity what? Decoupling. Now, why could I do that? Because this J11 portion that relates this one to this one is gone. Okay? Because this J11, that J12 portion of this matrix that shows the effect of these joints to this one is gone, and mutually you can see that these guys will have no effect on the omegas as well, right? And this is what we had, if you remember in the past. If you remember in the past, in the video when I talked about the inverse kinematics, if you remember when I talked about inverse kinematics, I told you when the robot has 60 OF and the wrist is spherical, I can break the 6 equations of inverse kinematics into 2 smaller sets of 3 by 3. The first 3 are called inverse position problem. The next 3 are called inverse orientation problem. I could separate these. I could decouple them. And this is the same thing. When the position and orientation of the end effector are 2 separate things, their singularities are also separate. Okay, it's called singularity decoupling. So now, if I have a 60 OF articulated robot, correct? I have a 60 OF articulated robot. These are the first 3 joints, and then here I also have my what? I also have my spherical wrist, correct? The question is, what are the total singularities for this 6th degree of freedom robot? You say, well, I separate. I look at the singularities of this spherical wrist separately, and I look at what? The singularities of the first 3 joints separately. And then whatever they have, the combination will be the total singularities of the manipulator. Now, the wrist, we discussed it earlier, if you remember, when we talked about Euler angles. I'll show you that. If you call the angles of these guys theta 4, theta 5, and theta 6, then singularity happens when theta 5, if you remember, was what? 0 or pi. When the middle angle is 0 or pi, if you remember, for Euler angles, we call it gimbal lock. But if the middle angle is 0 or pi, it means these two will align, and it means you lose 1 degree of freedom here for the rotation of the end effector. So the only singularity they have is the mid angle here, theta 5, is 0 or pi. But what about the first 3 joints? Well, it depends on the first 3 joints. What kind of first 3 joints do you have? Are they all RRR, or there are RPP or PPP, or what? The hardest one is RRR, this guy. For these first 3 joints, if you call them theta 1, theta 2, and theta 3, you can see that the portion of the J matrix for these first 3, which we call J11, looks like this. It's not hard to show. For that 60 OF, the J11, the portion for the first three joints on the end effector position is this guy. And now the question is, what is the singularities here? As I said, the singularity happens when determinant is 0, and this guy is a 3 by 3, so I can calculate determinant. I can calculate the determinant of this 3 by 3. It has a lot of algebra involved, but you can show that in general there are 3 singularities for this one available. Case 1, the last angle is 0, the last angle. Case 2, the last angle is pi, so it is completely stretched, this member, or what? Completely retracted back. And there is one other case here, and that is, if you remember, we talked about this, that your theta 1 can be arbitrary, but your theta 2 and 3 are such that your end effector, not end effector, the wrist point, falls onto the original z-axis. In this case, if you remember, we had infinitely many solutions for theta 1. Okay, so that is also another singularity. So in general, this robot has 5 singularities, right? 2 for theta 3, 2 for theta 5, and 1 for this combination of theta 2 and 3 that makes the wrist go on the z-axis. Now, remember I told you that singularities happen at the boundaries of the robot or inside it. The boundaries are what in this case? The boundaries are when theta 5 is 0 and theta 3 is 0, so this robot basically reaches the furthest point possible. If you make theta 3 pi and make theta 5 pi, this comes back as much as possible, trying to reach as close as possible to the base. That's also on the boundary. But this case here is not. This case here, theta 5 and 3 can be arbitrary. Okay, so these last 3 joints that are going to come here and be mounted on the wrist, they can have arbitrary angle, so your end effector, you might end up even here, okay, after these 3 joints. And clearly now it is not on the boundary of the workspace end effector. So this configuration corresponds to a point that is what? Within the workspace, and that's what we say usually the singularities are on the boundaries. Sometimes they are inside the boundaries of the workspace, and that is exactly this last case here. Okay, so hopefully I could clarify the notion of singularity for you. I know probably I explained a little bit too much, but since this is one of those topics that is a little bit harder to digest and exactly understand what's going on, I try to explain it with sufficient detail. Thank you so much. I will see you in the next video.